Can you see my slide and
Yeah,
can you hear me?
I see it and I can hear you very clearly.
Okay.
Okay, if you are ready, you can start your talk.
Thank you, Monchai-san.
Okay.
So I'm sorry I couldn't attend the workshop on site, but because of the user experiment in Kyoto University. So today I talk on the utilization of infrared free electron laser at Kyoto University. I'm Heishun from IA Kyoto University. This is the outline of my talk. At first I introduce our facility, KUFL, and next I introduce some of external user experiments. And at last I will summarize my talk. So this is a schematic image of our facility, KUFL. The footprint is 20 meter by 30 meter, and it has two accelerator-based light source, MIR free electron laser covering 3.4 to 25 micrometer in here. And another one is a terahertz coherent undulator radiation source. Sakon-san said it's super radiance source, but we call it coherent undulator radiation. It covers wavelengths from 600 to 1000 micrometer. And we have two solid-state laser sources. One is a picosecond monodropped laser, neodymium vanadate, and the wavelength is 1064, 532, and 266 nanometer. And another one is a nanosecond neodymium YAG laser, and it can serve the wavelength of 1064, 532, and 355, and 266 nanometer. And that neodymium YAG laser can drive the nanosecond optical parametric oscillator, and it is a wavelength tunable source, and it covers wavelength range from 410 to 710 and 710 to 2300. And we have three user stations for MIRFL. One is user station number 1 here, and it is used for MIRFL diagnostics and simple irradiation. And another one is user station number 2 located here, and it's the main purpose of this user station is a pump probe experiment. We can use picosecond laser and nanosecond solid state laser together with FL in here, and we can also use a cryogenic environment for the sample. We can cool down the sample down to 6 Kelvin, and we can perform pump probe experiment in very low temperature. And user station number 3 is for multi-purpose experiment. And we have a homepage of this facility. If you're interested in, please visit our homepage. And I started from the introduction of MRFL. This is an oscillator type FL driven by a normal conducting accelerator. It has the 4.5 cell symmetrical gun, and it generates 8.4 mega electron volt maximum energy and total charge of 2.8 microcoulomb per micropulse. And after passing through this section, the electron beam energy selection was performed, and only the good part of the energy spectrum is cut out by the slit, and the total charge reduced to the 700 nanocoulomb in here, and injected to the 3-meter accelerator tube, and further accelerated to 40 mega electron volt, and keeping the charge. And we perform electron bunch compression in here, and they shorten the electron bunch length, and inject the bunch to the 1.8 meter undulator, and make a FL lasing in this section using the 5 meter optical cavity. And this gun can also be used as a photocathode RF gun. In the latter part, I little bit touch this point. And this is a typical spectrum and typical macropulse shape of the FL. And this is a ranging condition around 11.6 micrometer. And we can do high power wideband operation and narrow band operation. This operation mode can be switched by changing the optical cavity mirror slightly, optical cavity length slightly, 10 micrometer. Then the ranging mode switches from high power wideband operation to narrow band operation. And we have this kind of current shape of the electron beam, and the FL start to raise and go up to the maximum, and after stopping the electron beam, then it's decay out to the zero. And the macropulse duration of the electron beam is around 7 microsecond, and the FL is 2 microsecond. And inside in this macropulse, 2856 megahertz rep rate micropulse are packed in this inside of this macropulse. And the maximum charge per bunch is 55 picocoulomb in our case, in harmonic operation. And this is a typical performance of the MFL. The parameter is macropulse energy and the wavelength. We can tune the wavelength from 3.4 micrometer to 25 micrometer, but the macropulse energy, total energy of the FL is not constant. It varies as like this. This dip around here and here correspond to the absorption in the atmosphere, water vapor, and also we can have the carbon dioxide absorption. This absorption can be avoided by filling the nitrogen gas or dry air into the transport beamline, so that we can use a very broad wavelength range like this. And the maximum macropulse energy was around 80 millijoule at 8.2 micrometer. And we can extend the wavelength region a little bit shorter by using second harmonic generation. These orange stars are experimentally obtained value using the second harmonic generation from 5 or 6 micrometer. And when we irradiate DUV picosecond laser pulses on the cathode of the harmonic cathode, we can generate photoelectron from the cathode, and we can get higher bunch charge than harmonic operation. This leads to the higher micropulse energy of the FL. And because the laser rep rate is less smaller than the microwave RF frequency, so that the repetition rate of the electron bunch and FL micropulse are reduced from the 2856 megahertz in case of harmonic mode to 29.75 megahertz in photocathode mode. This leads to the lower macropulse energy of FL. So this mode is good for nonlinear optical studies, such as high harmonic generation in solid material, which has already been observed in cave shell. This is set up for the high harmonic generation in solid in case of the zinc selenide, and we focus FL onto zinc selenide and observe the harmonics component by using the UV to NIR spectrometer. And here showing the results in the, we can clearly see 9s, 10s, 11s, and 12s harmonics, and wavelengths of the high harmonic generation depends on the fundamental wavelengths of the FL. We can tune the peak as like this. And I'd like to explain about the pulse duration of our FL at 10 micrometer. And these are experimentally obtained pulse structure in our facility at 10 micrometer operation. And you can see some specific pulse structure and the very narrow time widths. In case of subunique operation, we could get 230 femtosecond pulse duration in full width maximum, and this corresponds to the 6.7 optical cycles in this wavelength. And also, in photocasted operation, we can have even shorter pulse duration. It is 150 femtosecond in full width half maximum, and it corresponds to the 4.2 optical cycles in this wavelength. So, as Sakon-san mentioned, we can use a very short pulse duration in case of the FL. Sub-picosecond or femtosecond pulses can be obtained. And I move to the terahertz coherent undulator radiation source. So for developing this source, two Thai students, Dr. Shikuharin Spako and Dr. Shiriwan Kurainara, made a great contribution. I'd like to thank them for their contribution. And this is a 3D image of the source made by Shikuharin Spako. And the electron beam is generated from photocasted RF and perform bunch compression in this scaling section, and the compressed electron bunch is sent to the undulator and generate coherent undulator radiation in terahertz region. And when the electron bunch length is shorter than the radiation wavelength, we can get a strong radiation. And this is a photo of the system. There is an RF gun behind the solenoid, and we can, using scan, we compress the electron beam and focus electron beam by triplet couple and send it the electron beam to the undulator to generate terahertz radiation. And we insert tinfoil mirror into the vacuum and deflect the terahertz radiation and transmit the electron beam, so that we separate the electron beam and terahertz in here and use terahertz beam in out vacuum. And we constructed the interferometer for measuring the spectrum of this source, and we confirmed that the frequency tunability from 160 to 650 gigahertz. And also we confirmed that the 10 period radiation emitted from the 10 period undulator. And we performed the absolute energy and peak power characterization. And this is a graph for the total energy against the electron bulk charge. And this is the micropulse energy against the frequency of the radiation, and also peak power. So that in the lower band charge condition, the total energy depends the square of charge, as like this. But at the higher band charge condition, total energy is saturated due to the bunch lengthening induced by special force inside in the bunch. And then the maximum micropulse energy was around 1.3 microjoule at 0.16 terahertz. And the highest peak power was 38 kilowatt at 0.33 terahertz. The peak power was calculated by assuming the 10 cycle radiation. So next I move to the introduction of the external user experiments. So before going to the detail of the user experimental results and topics, I'd like to introduce the history of external user groups and their main field in our facility. So we started the external user program in 2011. At the time, the number of users was 3, and gradually going up to 18 in 2012, and this year one user reduced, and now 17 users in this fiscal year. And there is a different field characterized, and 5 from accelerator and light source development, and 1 from direct usage of electron beam, and 2 from laser processing, and 5 from biology, and 4 from material science. Not so big number, but because this facility is operated only by one person, me, so that is a little bit heavy load for me. And next I move to the introduction of the application experiment. The many application experiments have been performed in KFL, but in this presentation I will introduce following subject. Direct observation of selective phonon excitation by MFL, enhancement of anode reaction of silicon carbide by FL irradiation, visualizing a hidden trap in a novel scintillation material, creation of sub-wavelength laser-induced periodic surface structure, LIPS, and study on crystallinity of LIPS, and laser-induced degradation of cellulose and lignin, and single electron irradiation on scintillation material. And for the direct observation of selective phonon excitation, so that the sample 6-hexagonal silicon carbide 6H-SiC is placed inside in the vacuum and put on the cryostat and cooled down to 14 Kelvin. And we shoot FL to excite the specific vibrational excitation state, selected state, and probe the existence of the excitation by using the Raman scattering, using the nanosecond neodymium laser. So at cryogenic temperature, only when the vibrational excitation takes place, a peak can be observed in the anti-Stokes Raman scattering spectrum. And this is the result, and we could see the peak at a certain condition, and this is the indication of the selective phonon excitation by mid-infrared free-electron laser. These results are published in APL in 2013. And another user used this selective phonon mode excitation to process the material, silicon carbide. Silicon carbide is quite stable against the electrochemical process. And this property is sometimes good, but sometimes bad, and makes the surface processing by electrochemical process difficult because of the very stable. And the user irradiate FL tuned to the 3C SiC phonon resonances, and found some modification of the state or the condition of the crystal or SiC. This is a result of the linear sweep voltgram. They put the SiC sample inside in the electrochemical system and sweep the applied potential or voltage and measure the current flowing. Without irradiation of the FL, nothing happened. Very small current only appeared, but with LO mode excitation or TO mode excitation, they found strong current flowing due to the some modification of the sample by irradiation of the FL. And also, LO mode excitation, it corresponds to 10.8 micrometer, and the TO mode excitation, 12.8 micrometer, showed different results. This is also interesting. And they also checked the surface state by same scanning electron microscope after platinum electrolysis deposition. And TO mode excitation, they saw some sparse deposition of the platinum as like this. Only the irradiated area can have the platinum deposition, and the non-irradiated area nothing deposited. But in case of error mode excitation, they see this kind of specific shape of platinum electrolysis deposition. This also indicates T-on mode excitation and error mode excitation has different impact onto the silicon carbide. And next I move to the visualizing hidden electron trap in novel scintillation material. Gadolinium aluminum garnet oxide GAGG scintillator has excellent properties, high light yield, short lifetime, but it also has an undesired long lifetime fluorescence component due to defects and trapped electrons in defect. The user performed UV pump and FL probe experiments to determine the energy level of the trap. So in experiment, they irradiate ultraviolet 266 nanometer to GAGG crystal at 12 Kelvin in cryostat, and make electron trapped in long life non-radiative traps. And after that, the FL is irradiated to the sample and excite electrons in the electron traps, and then we could see fluorescence. This is an experimental result without FL irradiation and only UV irradiation. The fluorescence observed as like this, green line, and when shoot FL, additional peak appears due to the electron release from the trap to the conduction band, and the electron, once excited to the conduction band, can make fluorescence. So this is a FL-induced electron release and fluorescence from the GAGG sample. And using this phenomena and measure the fluorescence yield dependence on FL wavelength, they can tune the FL wavelength and see the fluorescence yield depending on the FL wavelength and determine the energy level of the trap as a 0.31 electron volt. This result was published in APL in 2018. And next I move to the creation of subvalence laser-induced periodic surface structure, LIPS. So it was known that the femtosecond laser irradiated to the semiconductor sample, the subvalence structure can be created. And in KFL, also we can create the subvalence structure in silicon, germanium, silicon carbide, and the gallium nitride. So irradiation wavelength is in this experiment 11.4 micrometer, and you can see the scale bar, 10 micrometer scale bar as in here, and these stripes are much shorter than 10 micrometer. So in case of silicon, 1.5 micrometer pitch, germanium 1.6 micrometer pitch, silicon carbide 2.2 micrometer pitch, and the gallium nitride 4 micrometer pitch. And sometimes we see this hollow shape due to the melting of the central part. When the FL intensity is too high and the lips created, but afterward it's melted and then nothing remained afterward. And they studied the threshold fluence of the period and period of the lips, and depending on the sample, and also they performed home-probe measurement using nanosecond neodymium laser during the lips formation. but unfortunately not yet published those results, so that I cannot show you this time. And the user also studied the crystallinity of the lips on silicon. They measured the crystallinity of lips on silicon created by titanium sapphire laser and mid-infrared free-electron laser. These are results of the image of the created lips. Left one is the lips by titanium sapphire laser, and right one is the lips by MIFL. And then they measure the user TEM and the X-ray from synchrotron radiation source to characterize crystallinity, and they found that the lips created by titanium sapphire laser kept a high crystallinity, but it has a slight strain, residual strain. And the MIFL case generates a defect, but strain are not observed. So that they concluded that the lips created by two different lasers has different crystallinity, and this could be related to the band gap and the photon energy of titanium sapphire laser and the mid-infrared free-electron laser. And I moved to the laser-induced cellulose degradation. And this was published in 2020, Energy and Fuels, and the one user performed the sequential irradiation of infrared FL to the cellulose, and found those efficient way to degrade cellulose. So one condition is irradiate 72 micrometer, and afterward irradiate 9.1 micrometer. Or firstly irradiate 3.5 micrometer, and afterward irradiate 9.1 micrometer. They measure the mass spectrum of the irradiated sample, and found some signature on the glucose and the cellulose generation from the cellulose sample. And he claimed that this leads to the future efficient generation of ethanol from cellulose in biomass sample. And similar experiment was performed also for lignin, biomass also. Lignin is a biomass, and this time irradiate 2.9 micrometer or 7.1 micrometer FL to the lignin to degrade to the sample. And 2.9 micrometer cannot be generated in our facility, so that another FL facility in Nishihon University was used for this purpose. And as a result of laser-induced lignin degradation, the user found the coumaryl alcohol, hydrated coniferyl alcohol, and vanillic acid in the irradiated sample. And they claimed that FL irradiation to lignin can release several low molecular weight aromatic compounds. So they used also the mass spectrometer to analyze the irradiated sample and mass chromatogram, and also they performed NMR analysis of the irradiated sample to identify the generated or obtained sample. And at last I introduced some exotic application with our facility. It is a single electron irradiation. So this is a parasitically use of the MIFL accelerator to study scintillator responses against mega electron volt electron beam. So we reduce the determining cathode temperature and defocusing the electron beam and use a small collimator. Single electron irradiation condition has been realized in some port of our facility, our accelerator. And these are spectrum, energy pulse height spectra of single electron irradiation of LISR scintillator. So you can clearly see 2 MeV isolated peak, 3 MeV isolated peak, 4 MeV isolated peak, and 5 MeV, 6 MeV. Those peak high pulse height correspond linearly correlated with the electron beam energy, so that they can characterize the scintillation material property against the single electron beam, a single electron irradiation in MEV electron energy region. So I came to the summary. I'm not so sure how long I talked, but I hope it doesn't take a very long time. And as a summary, I introduced MIFR and the terahertz coherent undulator radiation in our facility. And I also introduced results from user experiments in our facility. And I'd like to advertise that we call for proposal of user program. Our facility will start December and close middle of January, next January. The deadline has not been announced yet. We are accepting international users. If someone wants to use KFL, please contact me. This is my email address. Thank you for your attention.
Okay. Thank you so much, Sensang. I like the advertisement. Okay. Are there any questions from the floor? Oh, okay.
Thank you very much for the nice presentation. So from the point of view of a material scientist, I have a couple questions regarding your experiment. So you did use the FEL to study the gap system scintillator.
Sorry, maybe we changed the microphone because that one is not good.
Okay, sorry, bad microphone. Okay.
You mean this result?
Okay, yeah, we can hear you clearly. Can you hear me?
Yes.
Okay, perfect. Yes, about this slide. So the scintillator, according to your paper, was cooled down to 12 Kelvin, and I found it pretty amazing that you have like a trap state that lasts really long, that the emission had a delay of like a couple microseconds, and the energy scale is like only 0.31 EV. So I think the trap state it's got to be pretty deep in the material. So could you comment on the time scale that you detected? Is it from the response time of your equipment, or is it something that's like later fluorescent after the FEL was irradiated?
So that the detection system is a photomultiplier tube, so that the detector itself is a nanosecond or sub-microsecond time resolution. And the FL itself having the 2 microsecond pulse duration as like this, so that this UV emission induced by FL have a similar pulse shape as FL in this case. But if the trap state have much less electron than this one, or the FL energy is very close to the energy level of the trap state, the electron can be emitted, get smaller, and the pulse shape deformed, so that the number of electrons is not sufficient to follow this pulse shape of the FL, so that the some of the deformation of the pulse shape of the FL induced emission occurs. So that I cannot catch clearly what is your point, but
Oh, yeah, I think
Is it okay? Is it okay?
Yeah, the elaboration was clean. Yeah, thank you. I think that's the part where I didn't get at first. Actually, I have another quick question regarding your silicon carbide application. So actually, this is becoming hot because like people do EV stuff, and see silicon carbide is what people try to synthesize. Actually, there are a couple industry open in the northern part of Thailand. They're also trying to do this. So electrochemical process. So how long can this affect of the resonance enhance electrochemical process ability last? Does the FEL has to be shine like this entire time, and then you dip it into some electrochemical process?
This is we did the FEL regulation our facility, but the user took back it to their lab. One day after, or I don't know how long they kept without electrochemical processing, but they at least order of day, so that this is a kind of permanent change induced by some very strong photo excitation or phonon excitation, so that this is a permanent creation of some kind of defect in the surface area of the silicon carbide, and you don't need to care about how long. So,
I see.
If you heat it up and make annealing to refresh the surface, it could be kill the effect, but this is a kind of permanent. I say damage onto the sample. So.
I see. Thank you very much. That's really exciting. So if it lasts very long, then it could be manufactured as well. Yeah. That's cool. Thank you. ありがとうございました
Okay, thank you very much for the question.
About your experiment for the single electron aerations, I think several people have that question. How do you know it's single electrons?
So that if it's not single electron, at first it cannot create this isolated peak. And also, if we increase the number of electrons, we can see second peak around here. This is a this is a single particle peak. And we can also have two particle peak at the double height due to the two electron injected simultaneously, then the scintillation light yield is doubled. So this phenomena only happens when the single electron condition is realized. So that's why we claim or we say this is a single electron.
Okay, thank you very much. Thank you very much, Sen-san.
How much does it cost for the electricity for running the FEL?
So actually my facility is sharing the building with another ion accelerator and also electron microscopes. I cannot identify how much is the annual electricity cost for our facility. So I'm sorry, I have no data. So
Okay. That's fair.
But I should say, compared to the synchrotron radiation facility, the electricity consumption in mid-infrared free-electron laser is much smaller because the energy of the electron beam is 100 times less, so that the current used for bending magnet or acceleration is much less.
Yeah.
And also this is the pulsed device. Synchrotron is a CW accelerator. So that the pulsed device, then the duty factor is very small. So that the accelerator itself consumes energy consumption is much smaller than the synchrotron facility. So that the
Okay, should be much smaller than the synchrotron facility.
yeah. But the synchrotron facility consumes a lot of.
It's different scale. We couldn't compare it anyway. It's different scale.
Since you already said that your facility also share the same building with ion beam, I think it's tandem, right? Actually, in Chiang Mai, you know that we also have similar situation. Do you have some idea, or you already have some a kind of collaboration work that you use Free-electron laser and ion beam together?
Actually, we have no collaboration, and the ion beam facility will be terminated in next year, so no longer available. And now they have problem of the trouble in the accelerator system, so that now already it's stopped.
Okay, you just break her dream.
No, you can consider something, some collaboration.
Yeah.
But for us, no. Just I say.
Yes.
What kind of magnet that you are using for your KU field?
Which undulator or
This
bending magnet?
It's not permanent magnet, right? I have no idea.
Which magnet? Which component?
Undulator, yes.
Undulator. We use hybrid undulator. It is a combination of the vanadium permanganate and the neodymium iron boron.
This is permanent magnet, right?
Yeah, combination of the permanent magnet and the ferroelectric piece.
Do you need any cooling or something?
No cooling. No
Okay.
cooling.
Yeah.
So we don't have the electron hitting on the magnet, so that no problem for that. And also, it is out vacuum, not in vacuum undulator, sometimes used in the synchrotron facility, so that the electron passing through in vacuum, and we have a chamber wall and undulator, so that we have no heat input due to the electron beams. So no need for the cooling for undulator.
Okay, thank you.
Okay. Hello. May I ask you your facility? Do you have many non-academic users that coming to use the facility?
No. Nowadays, no. Used to be, we had industry people coming for the electron irradiation. And some of the users collaborated with industry, but I have no direct collaboration with industrial people. Some users used their study, or they got funding from industry and bring their sample to here and irradiate and put back. So that is one information for you.
Okay. So you don't have the service like people sending samples for you to do the measurement?
Yeah. Because of we set the machine time from June to November, middle of November, 5 months user machine time, and almost full of booking, so that I have no time to do such kind of service. And if I can get money by that and a lot of money by that and the duty is not heavy so that I also need to consider, but not yet such a proposal I have it.
Or is it because you run it yourself? There is only you. Right.
That's a big problem.
Yeah. So for 5 months, operating time per year, right?
No. After that, we should perform experiments for students and also our own research. Mm-hmm. So we have some funding from government for research program, and also I got some budget for my research, so that we should remain some time for our own research. So
I see.
Yeah,
that's also important.
Okay. My comment is about the facility in Chiang Mai. I think it's probably a good idea to prepare to do this kind of service. I think that's the only way that you can get the users from non-academic, from industry. They are not gonna go to Chiang Mai and do the measurement themselves. So,
I think in synchrotron they already have such kind of service. Is it correct?
Yes, we have that kind of service. It's necessary because I think the companies, they don't have people.
Yeah.
So but they have money. So
good.
Any more issue that we can discuss here? Okay, on the back there.
So for your applications, like your paper is really well rounded, and it has like the application ranging from the Rabi oscillation detection all the way through biochemical applications and even material science. So I think for Chiang Mai University to move forward, we also need those kind of users who are academic and also like previously mentioned from the companies and stuff. So what is your PR strategy to get people to know that like, okay, collaborations, this is good. I have silicon carbide. I should bring it to you, or like that. So maybe Ajahn Sakhon-sang could do a similar thing. So maybe I think that's the gap that we're trying to bridge here. So what did you do back then? Like, because the application is extremely wide range. Like,
how do you get people to know that?
So as I shown that we started from 3 users and gradually grown up to 18, so that the most of user came by the personal communication.
That is very important.
Yeah. So that some user have started from 3 users, but the one user have connection. It is like a tree, but this one branch get 2.
Okay.
Another branch get 3.
All right.
Another branch get 4.
That become a binomial.
This is a kind of growing up strategy.
Okay. Now,
of course,
we can even calculate when we can reach how many users, right? How long does it take? Okay. You provide a very clear picture.
Yeah, the fractals model, really good. Thank you.
But of course, advertisement is very important. Mm-hmm. Otherwise, nobody know where is which kind of facility. So that for me, that is a problem. I don't attend the workshop or the conference on chemistry or biology. so that I have no direct connection with the Society of Chemical Chemistry and the Society of Biology or Society of Medical. So it's very difficult to directly access. Then the user presents their result in some different their society, and then, as I mentioned, the branch increase the number of users.
Yeah.
But if you have chance, it's better to go send some person to the chemistry society or the biological or medical society to advertise your facility, what can be provided.
Okay. Yeah, from your last slide, maybe you get more proposal from Thailand in the next round.
Yeah.
Sensang, I also would like to ask, what do you think about the idea to give the support to your user? Because your facility also supports some budget to the user. Yeah, we also your user, so we get 2 years support already. So what do you think is important to initiate the user by have some budget for them to come to do experiment at KUFEL?
So it's very important so that some user don't have enough money to come and but if we can provide some travel expense using the user program, so the access to the facility getting much easier, so that the financial problem of the researcher in Japan is a little bit serious, so that I think it's important. And if you can provide some budget for travel expense, it's better to provide. So I'm not so sure your situation. But
your comment is important for us because we will collect all opinions. And we will submit this to the funding agency. So that's why I asked this question.
Okay. It's important.
Thank you.
Yeah.
So developing the machine is hard. Finding the user may be harder. Okay. Are there any more questions to Sensang? Because I think this is a very wide picture from the machine buildings to many applications. I would like to say that I didn't expect I would see a variety of the application like this, because normally when I talk to you, it's more like a radiation, right? And from what you presented here, I can see a variety of application from basic research to something going to the manufacturer. Yeah. So hope we can have this kind of applications happening in Thailand in the future, right? So if there is no more further question, then Sensang, thank you very much for your time, and you are very informative and inspiring presentation. Hope we can see each other maybe in Thailand. Yeah. Oh, next month you come to Chiang Mai. Okay. Then, okay. Thank you very much again, and have a good time.